All right, folks, we are back. We are studying section 4.21 on continuous input. So what are we even talking about? So remember, the whole point of this chapter is to look at linear models for classification. And in this particular subsection we're in, we're going to be taking a probabilistic approach to coming up with these linear decision boundaries. So in the previous few chapters, few sections, we've been coming up with some useful, but maybe perhaps a little bit ad hoc approaches to coming up with linear boundaries to distinguish one class of data from another. You're given some examples, and you want to divide them with a line. How do you do that? There were some kind of maybe intuitive approaches for doing so, and now we're going to kind of apply the probabilistic approach and see how we get those linear decision boundaries from that angle. Okay, so this is just kind of going back a little bit. So we're going to look at a probabilistic view of classification and show how models with linear decision boundaries arise from simple assumptions about the distribution of the data. Okay, and we're going to be using the generative approach. So we're going to be modeling the class conditional probability densities. We're going to specify what those are, and assume we're going to be given some class priors, and then use these to compute posterior probabilities through Bayes' theorem. And it's all really just kind of going to be a bunch of algebraic manipulations, but we'll see that in certain settings, this approach will also give us those linear decision boundaries. Okay, so that's the whole game. That's all we're going to be doing. The section, it's a little bit tedious, but it's all quite straightforward. Just some algebra, basically. Okay, so let's get on with it. So the class conditional. So let's assume that the class conditional densities are Gaussian, and then explore the resulting form for the posterior probabilities. So to start with, we shall assume that the classes all share the same covariance matrix. And to get those linear decision boundaries, that's what you're going to have to assume. What does that mean? It just means that your data they all have the same kind of spread. So they could have like different means, but this, maybe this is like your negative class, whatever it is. They can have the same means, but their covariances, they can have different means. So the centers are, different places, but their spreads have to be the same. This may or may not capture your data, it probably won't. But anyway, this is one way to get these linear decision boundaries. Okay, and we can see that. So when we're modeling these, class conditional probabilities, notice there's, what's the probability of x given it's coming from a particular class? Well, it's going to have its own mean, so notice the k, but the covariance is going to be the same for all of the classes. Okay, so how are we going to actually go and compute this quantity? And well, you can relate it. There's just a sigmoidal function that's going to come in, and it's going to have some parameters, but I think it'll be just useful for us to derive this directly. It's very simple, so you can see that there's no magic to it. So let's just do that. Okay, so remember what we care about is we want to get the probability. We'll do the two-class case first, and then we'll go on to the multi-class case. Okay, so remember this. We're going to use whatever the rules of probability, whichever ones they are that are relevant here. And now we're going to write this as P of x given C1. So that's our class conditional distribution. So how likely was it to come from that class? Multiplied by prior times the sum of those, right? Because it can only have come from two classes. Okay? And then what we'll do is we'll just divide out by the top, so by the joint probability. So it's going to be 1 plus P of x given C2, P of C2 over P of x given C1 times P of C1, right? And then we can just write this as, this is the same as x times ln of this. And now just for maybe to kind of make the focus on C1, we can just write it equivalently as 1 over 1 plus, I don't know why I switched to red, but okay, minus P of x given C1 times P of C1 over P of x given C2 over P of C2. And then we're just going to call this thing, we're going to call this A. Okay, so we can, call this, okay, so this is going to be like, 1 over 1 plus x minus a. We're just going to call this function, this is going to be a sigmoid. So it's going to look, you guys can still see. What does this look like? So it looks like this. So First of all, it's always greater than 0. And then this is at a. So when a is equal to 0, this function is going to be at 1/2, right? And then as a increases, well, this thing is going to get smaller. So you're going to approach 1. And as a increases, this is going to get very large. So you're going to approach 0. So you basically have a sigmoidal function, right? Okay, and that's kind of cool. And so, and this quantity, like you can think, oh, sorry, and I forgot this forgot a logarithm here. This is a minus ln. And this quantity, so a, which is, so let me just write it out again, just to, this is kind of a cool quantity, and maybe that's why he kind of goes into it. This is, well, we can again just write it again in terms of the, remember, the joint probabilities, again, ln, right? And it's equal to the, and let's just go on a new line, is equal to PC1, oops, not PC1, P of x, right? And these cross. So this is just a log odds. So the odds of the posterior probability, so the odds, the ratio of the probabilities, the posterior probabilities of the two classes given data. So as that ratio, and all we're saying is as that ratio increases, the probability of one class goes up, as you would expect, and goes down the other way. Yeah, so that's just already pretty cool. I mean, for me, working in neuroscience, this is cool. We have neurons have these kind of sigmoidal firing rates, so you kind of think of them as maybe they're kind of doing a classification, doing some kind of a tiny decision, and then you add up all these decisions together, and you get the human brain doing amazing things. Okay, but anyway, all of this was in the previous section. So now, what are we going to do in this particular section? Well, what we're going to do is we're actually just going to fill in. We're going to see what happens when we fill in this guy. Okay, so all we're going to do is, and let me extend this line so I can see. Okay, I'll go all the way down. Okay, so what we're going to do is we're going to say, well, now, so let's assume that P of x given C1 is going to equal to, there's going to be 1 over 2 pi to the, something, and then 1 over the determinant to the 1/2. Those aren't going to matter, times x minus 1/2 of x minus mu1 t x minus mu1. Okay, so now the important thing is that, the great simplifying aspect that gives us these linear boundaries is that is the fact that for P of x given C2, well, it's just going to be the same thing. So I'm just going to like copy it all down. I'll ignore the constants. So the only difference is that this becomes a 2. Okay, so that's kind of going back to our picture that we have. Let's say we've got our class 1 here and our class 2. So this is mu1, this is mu2, but the sigmas are the same. These the covariances are the same. Okay, so now the great thing is, let's just take the logarithms. So if we just take the logarithms, so ln of P of x given C1, again, I'm going to drop all it's going to be minus 1/2 of x minus mu1 transpose sigma minus 1, x minus mu1. And so you can do this lots of ways, but let's just say we just do it the straightforward way, right? Minus 2 mu1 transpose sigma minus 1 x plus mu1 transpose sigma minus 1 mu1. Okay? Great. And now when we've got so all we have to do is figure out what it is for ln p of x given c2 equals exactly the same thing. Right, more or less. No, exactly the same, except that the means are different, okay? And now, so now if we subtract these, because we want to get, equals ln p of x given c1 over p of x given c2, well, miraculously, we've got these squared terms showing up, but they actually cancel. That's the whole trick, and that's why we get these linear boundaries. Okay, so they cancel, and so what do we end up with? Well, we end up with mu1 transpose sigma minus 1x minus mu2 transpose sigma minus 1x minus mu1 transpose sigma minus 1 mu1 this is all correct, plus mu2 transpose sigma minus 1 mu2. Okay? And then there'll be a term for, and then we've also got, yeah, so I was just going to include the prior as well. So then when we want to compute this A thing, so then A is ln p of x given c1 times p of c1 over p of x given c2 times p of c2. Well, this is just going to equal to, so let's just write it nicely. So it's going to be mu1 minus mu2 transpose sigma minus 1x, right? Minus mu1 transpose sigma minus 1 mu1. I'm just double checking, did I have all of the signs right? Yep, the signs look correct. Plus mu2 transpose sigma minus 1 mu2. Very good. And then finally, we're going to be subtracting out, yes, right. So it's going to be plus the ln of PC1 minus the ln of PC2. We will just write this as. Okay. Good. So basically what we get is that so this is going to be called W transpose, and then this is going to be called WO. So we get that the probability of C1 given X is going to be the sigmoidal function of A, which is 1 over 1 plus X minus A, and A is a linear function, right? So A is going to be equal to some weight that determines on the depends on the difference between the means plus some constant. Okay, and this defines, and the larger A gets, so this is going to define some direction in space. This is W. This is going to be the line where, let's say this is the line where X such that let's see. So let's just consider the case where W naught is 0. So this is the point where X such that A is equal to 0. Given W. And so everything on this side is going to be, C1, and everything on that side is going to be C2. And now if you adjust W naught, so now you're essentially going to move this line forward and back. So if you if you increase it, then this line is going to move backwards, and it's going to make more of the space going to be C1. If you decrease it, then it's going to move the line forward. More of the space is going to be equal to C2. But the main point is that you're going to have this linear decision boundary that's separating the two classes. Okay, so the whole idea here is that, look, when we got these decision boundaries before, and we've done this, with Fisher's discriminant or doing kind of linear regression, whatever it was, the perceptron. Well, look, we can get it in a different way we can also get it if we assume that our classes have, a particular conditional distribution. Okay, and the key idea was that the sigma terms are the same and they cancel out. So these quadratic terms drop out. When it doesn't drop out, then you get these quadratic surfaces. So that the shapes, are just going to become curved, a bit more complicated. But the basic idea is simple. The algebra is exactly the same. You just don't get the cancellations. So you can't express things as simply. Cool. Okay, so the only thing, so now let's just do the multi-class case. The only kind of potentially confusing point, let's see if we can pick it up. Yeah, so this is, let's go back up. Okay. Yeah, so this is exactly what we got, right? So, yeah, we derived exactly this expression where we have defined W. This is exactly what we had, and then we've got the two contributions of the means and the relative proportion of the priors. And it's cool that as you would expect, if this prior for one of them goes up, then this kind of bias term increases, and it makes more of the space equal to class class 1, as you would expect. Okay, so we see that the quadratic terms in X from the exponents of the Gaussian densities have canceled. That was the whole idea, due to the assumption of common covariances. That this is a very important assumption, leading to a linear function of X in the argument of the logistic sigmoid. So that's the whole point, okay? That is the whole point. Yeah, okay. This result is interesting for the, so I think I think it's got a picture of it happening. So here we go. Yeah, there's kind of these two classes which have the same decision boundaries, and you get this nice kind of smooth surface going from one to the other. This kind of nice sigmoid that's going to be, I guess, like balanced along here, something like that. Okay. Yeah, so now, and then the multi-class case is basically, it's just basically the same idea. It's just, okay, so, sorry about all this. Okay. There we go. For the general case of K classes, we have, okay, so it's just, the only confusing thing is like what A's and the W's, they start becoming a little bit different, because you look at this, you're like, well, you want this to correspond when K is equal to 2 to the previous case that we had, and it doesn't quite, and it's just because he's parameterized it slightly differently. Everything the formulas are correct. It's just that the key point here, and we'll go into together, the resulting decision boundaries correspond to the minimum class, will occur when the two of the posterior probabilities, the two largest, are equal, and so will be defined by linear functions of X. And so again, we have a generalized linear model. Okay, so let's just read that again. So the resulting decision boundaries corresponding to the minimum misclassification rate will occur when two of the posterior probabilities, so the two, the ones that have the two largest are equal. So for a given point, you're going to rank you're going to have all these different classes. They're all going to give you a particular probability, and now you're going to see which classes have the two largest probabilities, and what decides is going to be the line where those probabilities are equal. So again, you're going to be kind of reduced to a two-class case, and we get the result that we had in the previous section. Okay. So let's just go and just derive that last bit. So it just becomes slightly different. So because we've got this. Let's just go and. Okay. Cool. So here it's going to be, what is C K given X? Well, now this is again the same idea, but now we're going to have multiple classes, right? So let's just call these I. Okay, and okay, so we're going to write this in its kind of softmax form. over sum on I, where these AKs are going to be ln of P of X given CK, P of CK. Okay? Now the question is, what are these decision boundaries when you have multiple classes? Well, those decision boundaries, so imagine what happens on the boundary, right? You have 10 different classes, but for 8 of them, the probabilities are relatively low, and you have 2, and the reason why why there's a decision to be made is that there's a tie, right? There's going to be a tie between 2 of those classes. If one of them was clearly higher than the others, you wouldn't be at a boundary, you'd be in one of the decision zones. So at a decision boundary, there's a tie between the 2 highest classes, okay? So at the decision boundary, there is a tie between the posterior probs of the 2 highest classes, right? That's why you have to make the decision. Okay, so we're just gonna figure out where those points are, and what's that generally going to look like. So let's say they just happen to be class 1 and class 2. We'll see that. So let's find the points where those probabilities are the same. So we've got P of C1 given X is going to be X A1 over this sum, which is not going to matter in a moment. And P of C2 given X is going to be X A2 given the sum, right? So if we set P of C1 given X is equal to P of C2 given X, that's going to be X A1 is equal to X A2. And so for these Gaussian situation where we assume the covariances are the same, that's going to be, we're going to drop the 2 pi's and the sigmas and stuff. It's going to be 1/2 X minus mu1 transpose mu1, right? And then there's also, I shouldn't forget the ln of P of C1 is equal to minus 1/2 X minus mu2 transpose sigma minus 1 X minus mu2 plus ln P of C2. Okay? And so we're just going to set these to be equal to each other, and we will get, so if this is supposed to be equal to that, you can just do the math, and you will find that the x squared terms will cancel out. So let's just do it. It's exactly the same computation as before, right? So this is going to be equal to minus 1/2 X transpose sigma minus 1 X minus 2 mu1 transpose sigma minus 1 X plus mu1 transpose sigma minus 1 mu1 plus ln P of C1, and we're just going to copy that out. Okay, it's just that these are going to be 2's. Okay, and then we set these equal to each other. That's going to cancel. That's going to cancel. And so you are going to end up with a setting where the decision boundary is going to be all the points where mu1 transpose sigma minus 1 X minus mu2 transpose sigma minus 1 X minus 1/2 mu1 transpose sigma minus 1 mu1 plus 1/2 sigma minus 1, you get the point, mu2 plus ln PC1 over PC2, all of this equals to 0. Okay, so just like before, so we're just going to call, this is going to be mu1 transpose sigma minus 1, just put it on here actually. Minus, and we're just going to call this whole thing, minus plus plus, we're just going to call all of that, right? So this is W, we'll call it W1, 2, or whatever it is, and we'll call it 0, 1, 2, or whatever you want to call that. So we end up kind of with the same. I mean, I guess his notation is slightly different, but you see that it's kind of the same. You get the same decision boundary. So it's kind of like you are getting the two-class case because you're ultimately making a decision between the top two classes, and it works in exactly the same way. So that's kind of how you get the linear decision boundaries also in the multi-class case. And again, it all crucially relies on having the same covariances. Okay, yeah. So yeah, just kind of a little watch out about that, but the idea is basically the same. For the general case, we have, so remember we're gonna encode things a little bit differently, and then these are the parameters for each class, but we see that the AK are again linear functions, the consequence of the cancellation of the quadratic terms due to the shared covariances. Okay, so I think it's yeah, I think okay. So I think what he's saying there is, yeah, okay. So it mounts to the same thing. I think what he's talking about is if you actually do this, if you actually write out, P of ck blah blah blah, is x, and there's going to be a 1/2. If you actually spell out all the exponentials, there's going to be an sigma xt plus all the junk on top. There'll be some junk that depends on k over a sum of x minus 1/2 xt sigma xt plus, and these junks depend on I. And the main thing is again, you can just kind of do the cancellation here if you want, but you end up at the same place. So you can kind of write, when you're writing these as, you can either write the full expression, which is kind of what I did in my derivation, or you can say, well, look, because the covariance are the same, I can cancel that out. I'm going to define my AKs as just taking the linear bit. Okay, that's all it is. But it's just the way you want it. Up to you how you write it. It's just basic algebra. The resulting decision boundaries correspond to the minimum misclassification rate will occur when two of the posterior probabilities, the two largest, are equal, right? Otherwise, there's no decision to be made. And so it will be defined by linear functions of x, and so again, we have a generalized linear model. If we relax the assumption of a shared covariance matrix, things get more complicated. To have its own covariance, then the earlier cancellation will no longer occur, and we will obtain quadratic functions of x, giving rise to a quadratic discriminant. Okay, so that's good to know about, but we're not going to discuss it here because we're talking about linear models. Linear and quadratic decision boundaries are illustrated in figure 4.11. So this is kind of a cool figure because you've basically got, for these two guys, they're kind of dominating the left half of this figure, and so the decision boundary between them, because they have the same covariance, it's gonna have the same shape. It's gonna be a line. But now these pairs, they're all gonna have different decision, these curved decision boundaries, just because their covariance are different, and so you can kind of see that kind of showing up there. Okay, cool. So I think yeah, I think there's just like a lot of algebra here. The main point was how you can get these linear decision boundaries in kind of this generative way. And one way it can happen is when these covariances are the same, and we've just kind of gone through the algebra of how that works. And in the two-class case, which can ultimately, when you have the same covariances, well, the two-class case, it will, when you have these linear decision boundaries, you end up getting these kind of nice sigmoids that go from one to the other. If the covariances are different, then you get the boundaries become more complicated. But again, hopefully that wasn't too tedious. I think you get the point. Derivations are quite simple, just taking some logs and canceling out those covariances. So I hope that was useful, and that I will catch you next time when we're going to be discussing maximum likelihood. So how do we estimate these parameters when we have data? Great. I will see you then. Bye.